back to thank the organizers for inviting me to give a talk at this very nice program. So, okay, let me start. So this is a kind of based on some part of a joint work cluster of coming with the following people, gang of Morin, Wang, and Graham. So let me start with some motivation. So the title of the program is called like this: Quantum Not Invariants and Supersymmetric gauge series. So I'm not going to talk about supersymmetric gauge series, but instead I'm going to talk about Fermionic finite group. So which are not supersymmetric, but they in some sense they are super. Because they are sort of Z2 gradient stuff. And the invariants which you have, they're not, I mean, one can call them classical invariant, but they are kind of quantum invariant because they actually can be obtained as in in terms of quantum field theory, topological quantum field theory.
But if there is a gradient, why you cannot call them supersymmetric?
Well, there is no Q. There is no Q.
There is no
Q. There is no supercharge.
But okay, I see.
But the Hilbert space is a super vector space. Okay, so let me start continuing motivation. Let me first start briefly mention something which is everybody here is very familiar with. So what is how do the usual quantum invariants, quantum not invariants, arise from gauge series? So we know that they arise as a combination in terms of Chern-Simons three-dimensional topological quantum field theory, which can be understood as a topological G gauge theory, where suppose G is a, if I take G to be simple Lie group, compact, and more assume that it's connected and simply connected. Then the value of this three-dimensional cyclic T on a closed three-manifold it depends on the choice of integer number which is called level, and informally it can be written as the integral over G connections divided by gauge transformations of exponential of let's say ik times Chern-Simons function. And here, this k is related to a quantum parameter which appears, for example, in case of SUN. When G is SUN, it appears this quantum parameter q, which is simply related to this level k in complex polynomials, for example. So how do I understand actually more invariantly this choice of level? So the choice of level, so for general G, also suppose it's a compact Lie group, but not necessarily connected, for example, and not necessarily simple. I should understand actually K as an element of H4 of a classifying space of my group G with integer coefficients. And when it's simple, something as simple like SU2, this homology group is just Z. And so this was observed by Dejean in the early 90s. And in particular, one can take G to be finite. And in this case, this homology with integer coefficients is isomorphic to a third cohomology of the G with coefficients either in U-balanced coefficients U1 or rational number is divided by Z. It doesn't really matter what you put here. And so in this case, one can use this fact to define so-called Dutch graph beacon n-dimensional TKFT, which is for which in order to define it, I have to fix G, some finite group, and I also fix an element of Hn of the G with these coefficients, Q divided by integers, or U1 if you wish. And so this defines, so this was a well-studied topic in the 90s, so this actually can be defined as a fully extended n-dimensional TKFT. But let me just write the value of the TKFT functor on a closed n-dimensional manifold. So for a choice of cohomology element nu, there will be the following sum, which can be roughly understood as this kind of finite version of this path integral. But in this case, it's a very well-defined thing because it's a finite sum. So I formally can understand the sum over maps from Mn to Bg. Consider it, of course, I consider this after homotopy. So currently, I can understand the sum over isomorphism classes of G bundles. And so there will be some simple factors, the number of elements of the automorphism groups of this G bundle time the following expression. I take exponential 2 pi I, I take a pullback with respect to G of my class nu, so I get an element of the cohomology of Mn, and then I can integrate it over Mn, which means pairing is a fundamental character. So again, this is something well known. But what we want to do, we want to consider fermionic or spin analog of such series.
Pavel, so you wanted to speak about not invariants, so phi it's only 3 manifold invariants, yeah, or n manifolds.
Again, this is, as I said, this is, in principle, you can define it as a full-fledged TKFT functor, and this will give you invariants of links or some high-dimensional links by the usual procedure. So you drill out tabular neighborhood and you consider the value, so you put, so then the value of the functor gives you some state, some element of the vector space associated to this boundary, and if you project it on a certain base space, this will give you a link value. So yeah, I'm not going to consider this, but like in the spin versions of these guys, I will discuss what is the corresponding invariance. Any other questions?
So Dybord-Witten theory are fully extended TKFTs, right?
Yes.
So what is the n category that you associate with point?
Oh, well, let me not comment.
Well, just a set of G bundles at every level, and then look at the corresponding one.
So over a point, this can be viewed as the n category. So
You have to think what n minus 1 work is.
So yeah, so since I'm a physicist, I'm supposed to give a talk to mathematicians. So I'll try to be formal. And
So
as far as I can.
I can ask you a question which I asked privately, but maybe it's worth doing publicly. So, how does one compute this action in general with a cocycle nu, if it's not trivial?
Well, like
Suppose I want a number in practice to compute it for some K3 surface.
Well, again, so one way is to use you can use a triangulation, but this is not good. The other, if you know the cohomology algebra, and so for example for abelian groups, you can if you know the cohomology, the ring structure of the cohomology, and you know the operations of Steenrod algebra, how it's actually not what is it as a modular of Steenrod algebra, you can kind of use this data to I mean, let me just give you a simple example. Okay, this actually 3 example. You're not okay.
Why not an example?
Well, Sergey will tell you that this is too trivial.
No, it's okay. It's actually will illustrate something.
But I'm not. I mean, this is some old like 1990s. Well, okay. There's actually some new development about the AGR fitness series. And but I'm not going to talk about.
But maybe just something absolutely trivial, like I don't know, Riemann surfaces for a manifold and Zn for a group. Yeah.
Well, let me take G. Okay, this is an example. G equals Z2, and so there is. Well, let me consider 3 dimensions. H3 is BG. Oh, sorry, H3 of BG is. Results is Z2, so there's two choices. One is trivial, the other is non-trivial. So I take a new kind of which corresponds to one, the one here that I can consider.
Can you explain that step also?
So what do you mean?
This computation. Yeah.
Sorry, this?
Yeah.
Well, this is RP. I mean, this is the H star is the H star of RP. So in general, for 3 manifold, it's something like this. So for nu equals 1 in this Z2. Integral by integral.
Sorry, we're coming to serious things.
But here is fine. Yeah.
Now you will repeat back everything you said before.
No, well, that was just motivation. So, okay, you have the following thing here. So so in general, 3 manifold, the partition function can be written like this. So you can just sum over elements. So the maps to 3 manifold to BZ2 up to homotopy, they are the same as the choice of H1 of M3 with Z2 coefficients. And then for each term here, I have each term is of this form. We just use a cup product of A on a 3 manifold. And for example, you can see that. Okay, for S3, let's see, for S3 this should be just, I guess, 1/2, right? And for something like RP3, it's a 0.
But Is there an example when it's a function of at least something?
Well, it's a
not
function
just,
of
not
new.
just a number. Yeah, but
Well, it's a function of nu.
no, I say you could take
I
a
relate it to
sequence of spaces or a Zn, or so that some parameter appears.
Well, you have a lot of discrete parameters. Again, you can vary a group, and you
Yeah,
can
so
vary.
this is what I am saying. Can you do this for Zn?
But I mean, why would I want to do this?
I just wonder what is known. So,
Well, you could.
if I put Zn, is there some
Oh.
general answer?
Yes. Yes. Very explicit. Yeah. Like for any, like even, I mean, for any abelian group, this is a very.
As a function of n, yeah? Is it a known?
Or I mean, if you fix a manifold as a function of n, yes, it's known.
Well, but in general, for general cocycle and manifold,
Yeah.
that's precisely why I'm asking this question. I don't think there is any.
Yeah. For general, no. I mean, yeah.
It's really hard. So even before getting to categorical things, even extracting numbers is.
I mean, I'm going to work with actually with just finite abelian groups, but one already can see that there are some non-trivial. I mean, you still get some, like physically you get some interaction series, and the corresponding invariants are not completely trivial. It's not the same as, even if I take just like finite abelian groups, the invariants are more refined than, for example, just U1, even just abelian transforming theory. They detect subtle invariants of links and three manifolds than just abelian transforming theory, even if this G is a finite abelian group. I mean, but of course they are way simpler than like SU2 transformers. But they can be used as a this series can be used as considered as the baby versions of kind of SU2 or SUN transformer series, where you can ask all this. So they're much simpler, but you can ask all those questions about categorification and so on. And maybe one can get some intuition about
But
this.
will the answer have something to do with John's polynomial, for example?
In certain series, it's these series are equivalent to a particular value of Chern-Simon series with particular value of level. Okay. So since there were some questions, I'm going to skip the definition. So I assume everybody knows what is a spin structure on a manifold. So.
But in terms of topology, say, so if you just do replaced by n, you will just it will be just depending on the h1 with coefficient in the n. So it will only keep like homological information about.
Well, it will, yeah, like not, but it will like as allow information about this h1 as a ring, essentially.
Okay, so
Well, for the n, it's not actually, it will more like as a modulo of a Steenrod algebra.
Okay, but still staying homological with,
Yes,
with the whole
yes.
ring structure. Okay. Mm-hmm.
Okay, but yeah, I want to consider fermionic spin version. So probably everybody knows, but let me introduce a definition, a bit of introduce a definition of spin. So n-dimensional spin TQFT. It's a symmetric monoidal functor from the category. So I will usually denote TQFT functors by Z. The functor from the category of n-dimensional spin Bordism between n-1 dimensional manifolds to the category of super vector spaces. And I will always work over C. So super means Z2 graded, and morphisms are even, so they preserve grading. And so there's a category of so where the objects are n-1 dimensional spin manifolds, and morphisms are Bordism between them. So the spin structure on the boundary restricts to the spin structure on the Bordism restricts to the spin structure on the boundary in the usual sense. And moreover, they should satisfy the following relation. So this grading is not arbitrary. So if I take evaluate this functor on the following closed manifold, where I take a product of some n-1 dimensional closed manifold times S1, where choice of plus minus 1 here denotes a choice of even or odd spin structure. This should be given to, depending on choice of spin structure here, this should be equal to either trace or super trace of the corresponding of one of the corresponding super vector space associated to this n-1 dimensional manifold. Okay. So another notion which I need is the notion of G equivalent.
What's the meaning of the index of Z?
This is a grading, choice of grading. It's again, it will be a functor. There will be a functor from category of Bordisms. The following category of Bordisms with maps to BG. So I will elaborate on this, to the category of vector spaces. So here the objects are pairs of n-1 dimensional manifolds and maps, homotopy, to be precise, homotopy types of maps to BG, and morphisms are pairs. So here this is a closed, and the morphisms are generally not closed n-1 dimensional pairs of n-1 dimensional manifolds, again equipped with maps to BG.
N-dimensional.
Yes.
N-dimensional.
N-dimensional. So morphisms between two pairs M1 F1 and M2 F2, but morphism between these pairs, so that the boundary of this guy is a disjoint union of these two manifolds, and the restriction of the map G here on the Bordism to the boundary components reproduces those maps Fi's.
So this is a TQFT with a flavor symmetry.
Yes. Yeah, there are various various ways to cook. I mean, this is probably not very canonical. I mean, sometimes it's called TQFT with symmetry G. Okay. And so another notion.
I think should I call it homotopy TQFT?
Okay. I mean, yeah, this is not a very. I mean, you can consider any topological space here.
Exactly. Yeah, this was his thing.
So invertible TQFT is a TQFT such that for any so the value on any n-1 dimensional manifold, which is a vector space, has dimension 1, and for all n-1, and also for all n-1 dimensional manifolds, the value of the functor, which is a morphism between vector spaces, is invertible. And of course, all these kind of three properties, being spin, being G equivalent, and invertible, they are independent, so one can combine them. Okay. So of course, we don't want. So we actually don't want. We have invertible TQFT because it's too boring. And we don't want to have G equivalent TQFT because this is probably too much structure. But there is a way to produce there is the following way to produce produce some non-trivial TQFTs from invertible G-covariant TQFTs. Namely, one can define the following map, which is can be called gauging, and it's a map between G-covariant invertible. So let me consider, so I will be interested in the case of spin TQFTs. To just spin TQFTs. So we'll denote the invertible functor by Z invertible and non-invertible, the corresponding non-invertible without this thing. So there is some one can explicitly define how you produce one functor from another. But let me just write how the functors are evaluated on when they evaluated on closed manifolds. So first of all, let me take. So in both cases, we consider n dimension. So first of all, if I if I want to calculate the value of the functor of gauged TQFT here on a closed manifold, this will be given by the following formula. So here, this is, since the closed is just some complex number, so I sum over all homotopy classes as in the graph-Witten theory of maps from Mn to Bg. I divide by this automorphism factor, and here I take the value of the functor of invertible TQFT, which is G equivariant, so it depends both on a pair, spin and manifold, and G, the map from Mn to Bg. And one can also write the value of the functor on n-1 dimensional manifold, which should be a super vector space. And this will be given by this following direct sum, where I will be summing the value of the invertible functor, which depends on this pair, and it's also some. This is a one-dimensional super vector space. So I sum over certain maps to Bg, but not all of them. So this here is, becomes a bit technical, so you can in principle ignore this. So you actually sum over a certain subset such that if you evaluate the invertible functor on the product of Mn minus 1 with S1, and with some map from this guy to Bg, it's is the same, should be the same for all G's, such that if you restrict G on a slice here with a fixed point on S1, this is a homotopy doing just F. So physically, you can understand that there's some sort of Gauss law constraint. And in principle, you can. So here you can write the relation between factors on general Borgisms.
Sum of all extensions of F to the M. So So I mean, you sum over all this G. It's all possible extension of your map from the boundary to Mn.
If it's on a trivial Bordism, yeah, yes.
What is invertible input?
Not really. You should be able to define this gauge. Well, it's important here when you derive this constraint, but it can be generalized.
But we know
I mean, you can do.
we know of lots of TQFTs with global symmetry that can be gauged.
Yes, yeah, you can do gauging. I'm not saying you can. You cannot. Yeah, you can do this gauging, but like the explicit formula will be a bit different. So I mean, this kind of condition. I mean, you can do this, but I'm not going to use this. You can do this. So here, yeah, you can define this without inverting. Absolutely. Okay. So, any questions at this point?
At what point is it important that this BG and not just arbitrary manifold?
At what point?
Well, I could define this with BG substituted by everything without any group structure.
Well, you can do this, but you have to be specified. So this, in principle,
Wow.
so here I define it only for G bundles, but I mean you can try to do this for general X. So instead of you kind of sum over homotopic. I mean you can modify it, but we are interested in G. So it's more relevant for like physics application.
But something will happen which depends on the group, yeah? So restriction to the group will be essential at some point, yeah?
Yes,
Not
yes. So explicit calculation will depend on the choice of group. And we will have to, to do some examples, we will have to fix some groups.
But it's also hard to compute anything if you replace it by...
Yeah. Like, because if you calculate homology of BG, you can use algebraic methods, for example. Yeah.
But instead you can take something much simpler than BG.
Oh, BG is simple. Well.
No, homology.
Well.
Yeah.
Yeah, I mean, it's a good, as Anna mentioned, there is a notion of these homotopy TQFTs, and so one can define this would be kind of some dynamical topological sigma, homotopy sigma model.
Can you say a little bit more how to relate this condition to Gauss law constraints?
Well, this means essentially these guys, they form some certain particular representation of this. Of the kind of automorphism group of F, and you only want to pick the kind of trivial representations. This basically means the condition means that this is a trivial representation of the forms a trivial representation of this G. Of G. There is action. You can define the action of G on these guys, and this is a condition that forms a trivial representation.
But it's the same. It doesn't mean it's unit matrix, yeah.
So what do you mean?
When you say that it is the same, so that is some matrix, yeah.
Well, it's the same because I mean there can be different choices of G such that it satisfies this condition. The statement that it should be the same, it shouldn't depend on the choice of G. I mean, if the group abelian, this is the choice. This is the difference is the choice of holonomy over S1, and this just defines the representation of. The representation of this, the whole G on this guy. So you calculate a character with a character of this representation with some insertion, and you demand this is just demanding that this representation is trivial. It's trivial one-dimensional representation. So in general, for non-abelian, you don't have the full G action of the full G. You only have some. So you pick some commutant of yeah, I don't want to go into detail. Okay. So any question?
There are no fermions at that part yet.
Well,
They can be, but not obligatory. Yeah?
here this part is not really important. This was spin or not spin. But okay, the question. So we see we can produce non-trivial TQFTs if we have if we know some interesting invertible TQFTs. And so in general, the classification of TQFTs is hard, like in arbitrary dimension. But invertible is actually possible to classify, which at least with some conditions. And this is a result by Fred Hopkins, and also which is a kind of formalization of a proposal by Kapustin. So this is I'm not going to use the result in most general form. I will just use the kind of what follows from this result for my goals. So from this theorem, it follows that the space of so-called fully extended reflection positive. So you can, if you want, you can ignore this for a moment. Invertible G covariant spin TQFTs. So you can understand this is some particular subset in a space of all invertible G covariant spin TQFTs. So this is fully extended. Okay, means it's a functor fully extended. Physically, this means that the series is local. In reflection positive, this is some some kind of more precise statement of unitarity of the theory, like weak rotated notion of unitarity. But so first of all, let me mention that this. So I forgot to mention that the invertible TQFTs form an abelian group under tensor product. Which means the value on n-1 dimensional manifolds, I get a vector space which is a tensor product of vector spaces, and the functors is also, I take a tensor product. For closed n manifolds, I just multiply the value. So they form an abelian group. And first I want to consider this modular continuous deformation. And I want to consider only torsion part of this abelian group. And the second, this is equivalent as a is isomorphic as an abelian group to the following abelian group. So a space of homomorphisms of the torsion part of the n-dimensional spin Bardism group of BG to Q divided by Z. So this is so what is this group? So what is the group here? So as a set, it's defined as a pairs of spin Mn and maps from Mn to Bg modular equivalence relation, where I declare manifolds to be equivalent as they are related by n+1 dimensional Bardism with a map to Bg again, so that on the boundaries the boundaries of this n+1 dimensional manifold is a disjoint union of pairs here of equivalent manifolds here, and the for equivalent pairs, the F's should be given by restriction on the bound of G on the boundary. So you can understand this is the objects. Sorry, the generators of this group are objects in the spin BG Bardism category, which I considered before, and you just quotient over all morphisms of this category. And the abelian group structure is given by disjoint union. So if I want to add up classes corresponding to pairs, I just consider class corresponding to its disjoint union. Okay, so this is some.
But sorry, what all this means? This means that you can change the formula at the left in the left corner and introduce parameters from this home.
Yes, yes. This means that for any, if I take any element from this guy,
so
this gives me some spin to KITP.
What happens to this formula?
I mean nothing. I mean this just gives me this index. So I can take any guy here in this deformation class corresponding to a fixed element here.
But you should say what is that in yeah?
Yes, exactly. That's what that's the goal. So you cannot just use this theorem to say anything concrete. You have to do at some point. You have to do some calculation. And
What is torsion part of?
well, torsion is just elements which are multiplied by some number and become trivial, by some integer number.
But this is an explicit theorem, like.
Yes.
I mean, there is a construction, so given any element.
Well, yes, but it's a bit implicit.
Okay, so you can construct me n category.
Well, it's I mean already for simple stuff, like say what is this like what is extended to KITP explicitly is a hard thing. Well, at least.
Can you deduce perhaps a non-extended one?
Well, yes, you can. That's what I'll say. There is a way to kind of obtain kind of. So you kind of. There is. I will mention.
So Pavel, this is an equivalence between the comes from the torsion part on the right and the torsion part on the left.
Yes.
Do you know anything about the free part in either case?
There is a conjecture about free part.
Okay, and the conjecture is presumably that the free parts also agree, but it's harder.
No.
No, it's different. Okay.
Well, okay. If you wish, if I erase torsion here, there should be something like. This is a free. This is a anomaly polynomial.
Sure. Okay.
But just educational question. So I'm confused with your statement. Fully extended means locality. What is locality for topological theory?
Well, so you can. I mean, there are different ways to formulate. So one way, I mean, if you want to kind of generalize the notion of usual TKFT, like for n manifold, you get. Some. For closed n manifold, you get some number. I'm being very schematic here. For n-1 manifold, you get a vector space. If you want to extend, like for n-2 manifold, you should get some one category, and so on, two category, and so on. But with some particular relations. But you also can formulate it as you just extend this notion of Bardism to n category, and you extend it as a function, as a functor to some. As a monoidal, symmetric monoidal function between some n categories.
But what is the restriction which you impose on all this?
That it can be fully extended.
It can be done, yeah?
Yeah, it can be done in a self-consistent way. There is it's not an arbitrary assignment. There satisfies some relation. So what I'm going to do, I'm going to take actually. If I want to consider. So actually, suppose I erase torsion here, and I take an element. I will actually want to fix an element from this guy. And one can make a statement that one can actually realize some TKFT labeled by this element here. So there's a map dual to inclusion of the torsion subgroup. So yeah, one can actually realize some representative in this in this deformation class labeled by just element of this guy. So this space, if I take U1s here, this space can be understood as a space of connected components of this space. If I take U1s. So, okay. So in particular, so one can make a statement like suppose I have this fixed element mu. What is the value of this invertible 2KFT on closed N manifold? Closed guy. So this will be just exponential of 2 pi I mu evaluated. So this is invertible equivariant. So I have this choice of bundle of a pi, mu evaluated on the class of the pair in this Bordism group. But of course, I mean, you still have to answer what is the so in order to make this more explicit, you have to specify actually mu. You have to way to explicitly calculate this mu. So mu is can be understood. Mu is a choice of mu is a choice of Bordism invariant. That is a map from this Bordism group to some torsion group. Okay. And of course, there is a question of this, like how do you define this for not just a value in a closed manifold, but as a TKFT functor, even non-extendable. But this can be answered in principle. And then the gauging will give me, so from this invertible G equivariant TKFT, this gauging operation will produce some non-invertible TKFT. Good. Questions?
So I guess this result is telling me that if I take the dimension to be 1, then there's exactly one torsion class, which is the non-bounding spin structure on this circle. And so it's telling me there should be one fully extended theory in dimension 1. I think the BG doesn't matter so much in this case.
I'm going to, just
You're going
a
to tell
second.
me what this is?
Yes.
Okay.
So the question is actually how to make it explicit. One has to calculate these Bordism groups. So the theorem doesn't tell you how you actually calculate this, and calculate Bordism groups and calculate the corresponding invariants, mu's, which are elements from homes, gives you a home from Bordism group to U1. So let me first mention the kind of zero example when G is trivial. So this is a classic result, probably by Milner. This is a spin Bordism groups of a point. So again, I forgot to mention this, the notion of the question of classification of this invertible TKFTs has a very important condensed matter application. So this invertible TKFTs physically they can be understood as fermionic symmetry protected topological states. And the part of our work was actually about this relation to condensed matter business. Okay, so the groups are like this. So you can you can recognize real chaos theory here, the coefficient of real chaos theory here in the beginning. So what is the manifold generator? So what is the spin manifolds in the corresponding dimensions which realize these generators of these abelian groups? So here it's just a point. Here it's S1 with odd spin structure. Here it's a product of S1s with odd structure. And so here there is nothing. Here it's a case 3 surface. And what is the corresponding Bordism invariance? Which can complete Bordism invariance, which can you can evaluate them on any manifold, spin manifold, and it will tell you in which element of the Bordism group it corresponds to. So here, okay, this is something trivial. I'm not going to write. So here there is no kind of universal notation, but let me denote this invariant eta. So for a closed circle, it just assigns you plus or minus 1 depending on the order even structure. So here, so one can take any Riemann surface, spin Riemann surface, and the corresponding invariant, which is Z2y, it is what is known to be Arf invariant. So here is nothing, and here is a signature divided by 16. So, in particular, it follows from the theorem of Reed-Hopkins there exists fully extended two-dimensional spin KITP. So here it will be just invertible. There is no gauging possible, such that if I evaluate it on a closed manifold, spin manifold, it gives me -1 to the Arf invariant of the spin manifold. And indeed, in this case, one can actually understand this in very detail. So what is assigned to circles and what is assigned to a point.
Is that some theory that's familiar?
Well, this is Arf to KIFT, I don't know. I'm not sure. Well, it's like for a circle, it assigns just one dimension.
Is it lattice or continuum modulars?
Or, yeah, I'm not very familiar with lattice construction, but I think there are some ways to do some lattice construction. But I mean, you can also, if you wish, you can in a sense, you can understand this Arf invariant as mod 2 index. So you can understand there's some sort of negation out of massive fermions.
It's the most democratic invariant. It's democratic invariant.
Okay.
Because it's sum of all.
Yeah, I mean, oh, you mean to define it in terms of this quadratic enhancement? No, yes, you can do. Yeah.
So is there any Z2 graded Frobenius algebra associated with this spin frequency?
Yes. Well, I mean, this is just essentially Clifford algebra with one generator.
Right, so the Hilbert space on the circle is one-dimensional.
Yes, one-dimensional, odd or even depending on the spin structure, and to the point you associate in like category of models or the Clifford one.
Does it mean that without a group in 3 dimensions you get nothing?
No. Well, yes, exactly. But we want so in 4 dimensions the torsion part is also trivial. There is nothing. But we want some group to get something interesting here. And so one needs to do this calculation of groups and Bordism invariance for higher G. So and this is what we do like for various choices of G in our work.
Sorry, so the thing sitting in 4 is the anomaly of transiments?
Yes, because the 4, as I said, it should be like the pre-part you should shift. So this is just gravitational anomaly in 2D. This is transiments to KITP in 3D, which corresponds to gravitational anomaly in 2D. Is it good? Yeah, just gravitation. So let me briefly mention how actually you can approach this calculation of this group. So let me suppose G to be abelian, and suppose this has no odd torsion. Then one can use the Adams spectral sequence to calculate it. Namely, there is a spectral sequence with t minus n as going to n, where I start from the second page, given by the following doubly graded extension groups. So this is, I write a general statement, which one can use for general Bardism group of extension between cohomology of spin Thom spectrum and wedged with BG with added disjoint point over Z2 and Z2, where I consider those guys as a model or as a models over Steenrod algebra. And these two grading, one grading responds to the length of your extension, and the other grading responds to a shift of grading here. So it's combined with the length and height of the extension. But for you can actually, for small t minus s, you can use some fact about, you essentially use the fact that this M spin is related to KO, connective real K-series spectrum. And so you can actually relate it to more manageable groups, which are extensions over just some part of Steenrod algebra generated by SQ1 and SQ2.
Sorry, who is M spin?
M spin is a Thom spectrum.
Atom spectrum.
Associated to the spin lift of this to this lift. And so you end up actually calculating just extension of between cohomology of BG and the trivial module by Z2.
So where did Z2 coefficients come from?
Well, this is a statement about Adams spectral sequence. So this is a Steenrod algebra is defined for cohomology with Z2 coefficients. And we use the fact, so in general, this will give you just some two torsion part, but since the G has no odd torsion, this gives you everything. So in principle, one can write the generalization of this Adams spectral sequence for kind of P prime part of, P prime part, but it becomes more complicated. Yeah, there's a version for like a homology with ZP coefficients where P is some prime number. So I have half an hour more, right?
Yeah.
Good. So I was told that if you give a talk to mathematicians, you should say some theorem. It's a theorem that.
Second one.
Well, yeah, this is by the people who I mentioned in the beginning, and myself.
You cannot avoid it.
I mean, there are two parts of this theorem. So first you can calculate, just calculation by theorem. So one thing I mean is the calculation of these groups for various G's. So you can find kind of more complete table in some upcoming paper So let me just list some relevant part, just to give you some flavor. So here is the choice of G, and one can write something more here, some other examples. And so it will be, for example, of this form, the product of Z8 to some power, Z4 to some power, and Z2 to some power with some polynomials. So this is not very important. And here it will be, because Z times the Z2 to some power. So in lower dimensions. So here, for example, it will be Z2 cubed times Z8. Z4, here it will be and so the other part is you can write complete, so explicitly write complete Bardism invariance, which gives you kind of a way, a good geometric calculates the class. So if you're given some pair of manifold and G bundle, it gives you a way to explicit way to calculate to which Bardism class it belongs. So there is explicit way to calculate this kind of value of the TQFT functor, at least on a closed manifold. Okay. So I'm not going to list. So again, you can find this in the paper or in the paper. So let me just list you a couple of interesting Bardism invariants, which corresponds to two Z2 subgroups here and here. So I'll take example to be G equals Z4 squared. And it's actually interesting that it's not enough to take something like Z2 squared to get something interesting in 4 dimensions. So you actually can show that if you just take Z2, this is just the same as H4 of BG Z1 coefficient. So here you actually just get your ordinary Dutch graph-Witten series. You don't get anything interesting. But here you get, you don't have just, you don't reduce just to Dutch graph-Witten series. Okay, so when I consider a map from n manifold to BZ4 squared, I can understand this equivalent, the F as a pair of F1 and F2, where each component is just element of H1 of Mn BZ4 coefficients. So in dimension 3, one can write the following Z2 valid Bardism invariant, which I will denote as mu3. 3 means dimension 3. So for a pair of M3 and F, it gives me the following value. Eta of, so we'll elaborate on what is the meaning of components here. And for mu4, for 4 manifold and map to BG, get a value of F invariant evaluated on the intersection of Pentragial duals of F1 mod 2 intersected with Pentragial dual F2 mod 2. So what do I mean actually by Pentragial dual here? So Pentragial dual, what I mean by Pentragial dual of A, where A is some element of H1 of Mn with Z2 coefficients, it's is a smooth submanifold in Mn of course, it should be codimension 1. It's a codimension 1 submanifold, which represents Poincare dual class in H n minus 1 and minus 2 dual to A. And the statement, there is a statement, the known statement that such class, one can always choose such. It can be always represented by smooth submanifold in the case of H1 with Z2 coefficients. So in general, of course, it's not true. It's not for arbitrary element of cohomology. It's not, of course, true, but in this particular case, it's true. So how do so this defines me some codimension 1 submanifolds here and here, and so I want to intersect them, but then I have to evaluate this. So this is the invariant of spin manifold, and this is the invariant of spin 2 manifold. So I need to tell you how I define a spin structure on this intersection.
Pavel, maybe you could say a word about the map you just erased that went back to the classification by homology classes in VG. So I can see that if you use the theorem that some homomorphisms out of this spin-Bordism group define some TQFTs, then there's a class of TQFTs coming from those homology classes that you gave before.
Yeah.
But I can't see the map on this side of spectra, and I don't know whether it's just forgetful, injective, surjective. I mean, this should give a finer classification.
Well, on the map of there is a map from KO to HZ. It's small. I think you can realize it like this. But I mean, it's M spin at low degrees is the same as Q. But you also can do it more explicitly. So you consider the map from Mn to, I guess, any x spin to Hn of x. And so how do we do this? So here you have a pair. So these guys are represented by elements here represent a pair of n manifold, and the map f from Mn to x. And so here I want to take the push forward of Mn.
Sure, that's well defined.
And the thing is that the Pontryagin duals of these guys, they will be just a cohomology with U1 coefficients.
But you forget the spin structure in doing this, right?
Yes, sure. Yeah, this is by no means injective. Or actually, it's not even in low degrees. It's surjective, but actually in high dimensions, actually not even surjective.
Mm-hmm.
Is there some reason that you should have expected beforehand that the answer only depends on F1 and F2 mod 2, or is that just?
Well, I'm not sure. I mean, kind of from this Adam spectral sequence. But, yeah, because you need, I mean, the important thing here is that you actually want, so if this is arbitrary element of H1 with Z2 coefficient, in general, this manifold is non-orientable. But if it comes from mod 2 reduction of element of Z4, it actually can be chosen orientable. Okay, so so how do you how do you define? So suppose you have locally looks like suppose I want to say that this is my x, which is some intersection of these two submanifold. So locally, locally x looks like this, and it comes from intersection of this Poincare dual of a F1 mod 2 and the other guy which is Poincare dual of F2 mod 2. And so you see this is this induces me some framing on, so gives framing on a normal bundle of X in Mn. And then it follows, like, using this framing, I can induce spin structure from Mn to X. So this is the same construction holds here and here. So I get some spin here, I get some spin 1 manifold, again I calculate eta this invariant which is equal to 0, 1, mod 2, and here I get some spin 2 manifold, and I get this alpha invariant of the spin 2 manifold which is also Z2 valid. Okay, so this gives me some invertible TQFTs which you can gauge, and so gives spin TQFTs U3 and U4 in respectively 3D and 4D. This is after I gauged with the corresponding convertible TQFTs. So again, one can define them, consider not just define them on the closed manifold, but one can actually understand them what are they as the functors. But let me go in a bit different direction. So this 3D and 4D TQFT, they define invariants of links and correspondingly surface links. And one can show that this invariance that can be related to so-called Sato-Levine invariants. So how TQFTs define this invariance is, again, as I already mentioned at the beginning. So if you have some link, you cut out its tabular neighborhood, and so you get some. So the TQFT gives you some vector, some element of the vector space associated to the boundary, and you can project it on a certain basis element. So you can choose some basis. So what is the Sato-Levine invariance? So for people who know them, you can already see them in the related to this invariance. So the Sato-Levine invariance, they can be actually defined for a general. So take me a bit more general, not just in 3 and 4D. So let me take n minus 2-dimensional. So this will be some hyper. Let me call it hyper. I'm not sure. Hypersurface n minus 2-dimensional hypersurface 2-component. What is called? So I want it to be semi-boundary. I will tell you in a moment what it is. Link in. So I consider them in an n-dimensional sphere. So again, when n equals 3, this is some link. So it has 2 connected components. So the semi-boundary means essentially, by definition, this means that there exist Seifert, volumes, Vi n minus 1 dimensional, such that, of course, their boundaries give me these link components, and such that the intersection of Seifert surface with another link component is empty. So in particular, this means that in 3 dimensions, this means that the linking number is trivial. So then one can define the n-dimensional Sato-Levine invariant So it will be valid in a space of semi-boundary links in Sn, define it as here. Of course, modular ambient isotopy. And the value will be in nth fundamental group of S2. But you also can further kind of compose it with stabilization map and consider its value in n minus two-dimensional stable homotopy group of spheres.
Is it intentionally called SLN, or is the fact that it's called SLN?
No, sorry, I'm not sure. This is not a like usual notation. I think the usual notation is beta. This is Sato-Levine.
Yeah.
And so
people algebraically split link. So this
yeah.
for n equals 3, so perhaps I.
Well, yes, yeah. I mean, in three dimension, you can actually define it more, more generally, kind of on a range in Sato-Levine, which is valid for proper link. You only require that the intersection number is even. But don't go into it. So the value. So I take a link and I take the class. So I take the intersection, the intersection of two Seifert volumes, and again by the previous picture, this intersection comes with the Fermionic normal bundle. So this means by the usual Potaragin-Tom construction, this defines me an element in this homotopy group of S2. And so why this is related to some spin series? But this is actually we know that in n equals 3 and 4, this group is the same as spin Bordism group of a point. There's a canonical identification. Okay. And then one can make more with the following statement. This kind of four-dimensional Sato-Levine invariant, in a certain sense, categorifies the three-dimensional Sato-Levine invariant. What does it mean? So first of all, we want to extend it to the functor from the category of link Bordisms to supersymmetric vector spaces. Super vector spaces. So how do you do this? So first of all, the value of SL4 on so understood as this functor on some three-dimensional link in S3. Sorry, one-dimensional link in S3, just the usual link. It will be given by, so this is something relatively trivial, but still not absolutely. So it will be either even or odd one-dimensional vector space, depending on whether three-dimensional Sato-Levine invariant, which is here just a number, equals to 1 or minus 1. So here I understand the Z2 value. So this in both cases this is Z2, and I understand the value as valid in multiplicative Z2. And so if I want to the value of the functor on the on some link Bordism, so I take so I extend it to so it will be some two-dimensional two-component link, not closed, but ending on this usual links on the boundary. And again, I can consider so there will be two components, L1, 2, and L2, which are two-dimensional. I consider Seifert volumes, corresponding Seifert volumes, so that dv I is equal to so this will be three-dimensional guys. And this will be the value of this arc to KFT, which I mentioned in the beginning, evaluated on this intersection of the effect volumes. Again, so in this case, this invertible TKFT can be very well understood as a full extended TKFT. Okay, so natural question to ask. So if the corresponding link invariant categorify, like the four-dimensional link invariant categorifies three-dimensional link invariant, so does this the full series, full TKFT categorifies this guy? So can we do this categorification for three manifolds, for closed three manifolds? Does this four-dimensional TKFT categorifies the three-dimensional TKFT? So what would this mean? So one can consider the categorification of this four-dimensional TKFT, so which gives me, so I can consider the functor which I will denote by z mu4 with index plus minus. So this will be some three-dimensional spin TKFT. So that if I calculated value on a certain manifold and minus dimension, like three-dimensional, two-dimensional.
You mean U3 probably?
So yeah, this I can calculate on three or less dimensional manifold. And to obtain this value, I use this functor evaluated on this manifold times S1 with order even spin structure. In particular, this would mean, so this would produce a certain relation between functors, and in particular, I'm not going to write like the general relation, but in particular, it would produce a relation of this following form. So the value of this three-dimensional TKFT on a closed spin three manifold, which should be just a number, since this is mu4. Since it's a three-dimensional TKFT, it should be equal by should be equal to dimension of the value of four-dimensional TKFT on M4 plus minus dimension of the first component of the supervector space, associated to M3. And so one can go down. So the value of the three-dimensional TKFT on a closed, let's say closed two-manifold will be given by Grothendieck group. Tensor with C, of course, of the category which is associated by this four-dimensional TKFT to M2. And so when I tensor, there is some choice of gradient here going on, and this choice of gradient will depend on this choice of plus minus here, and so on. But of course, one can immediately notice that this is not like this is exactly not possible to do because, for example, this is cannot be equal to just three-dimensional TKFT labeled by this element of Mercier, of three-dimensional Bardism invariant on M3, because this is in general some rational number. It's not an integer. So in particular, for example, if the value of this guy on a three sphere is 1/16. So at least naively you cannot do this, but you can make. So the answer is to this question is almost. So how do you? What is the relation? What is the precise relation? Is that so in order to formulate a result, so one can define the notion of direct sum of TKFTs. So we know there is an obvious kind of operation which is a tensor product of TKFTs. There's actually also operation which can be also the direct sum. And so let me not give you the full definition, but it's essentially determined by the following fact that if we want to take a sum of two TKFT functors and evaluate it on so this is n-dimensional TKFTs, evaluate it on a manifold which has exactly one connected component, then this will be a direct sum of the values of the functors. But you can extend it to kind of operation on the complete factors. Okay, so and then the statement that those decodified four-dimensional TKFTs, they're related as follows. They can be expressed as follows. Where these coefficients are understood in terms of a direct sum. And the labels here, so here this is the labels here are elements of certain elements of Hom of omega 3 spin of BG, where again G is still Z4 squared with E1 coefficients. So mu3 is an element which I introduced before. 0 is a trivial element, and mu3 prime is as an invariant. So again, it's the choice of the label, the choice of the Bardism invariant. And in this case, the Bardism invariant takes a pair of three-dimensional manifold and map to this F, which is F1, F2. Fi belongs to H1 of M3 with Z4 coefficients. It gives me kind of similar, the think of a similar flavor, Arf invariant of just Poincare dual of F1. So you can kind of you cannot categorize this kind of directly as a full three-dimensional TKFT because okay, it gives you. I mean, at least if you define. I mean, you want to understand the trace in the usual sense because it takes the value of rational. It takes rational numbers on closed C manifold. But there are some particular combinations of three-dimensional TKFTs which can be categorized in this sense. Okay.
I'm sorry, I cannot read this. This is F1 as an element of H4.
Sorry, sorry,
H1.
being sloppy here. H1. H1 of M3 with Z4 coefficient.
So I see that 4 plus 12 is 16.
Exactly.
Does it mean that Z0 is also rational? The values of Z0, are they also 1 over 16? No.
Yeah, yes. Yeah, the value on a 3 sphere, it's for any mu, it's actually 1 over 16. Yes. Yeah, for sphere itself, it doesn't depend actually. Because there is no homology.
This was a presentation for mathematicians. In principle, does it have a version for physicists?
You mean about symmetry protected topological
Not
phases?
just this whole story. Can it be presented to physicists also?
Yes, I mean.
It just.
I mean, this actually has some valid
Theoretical
physical application in condensed matter. Yeah, I'm going to stop here. Thank you.
More questions?
So it seems like if you consider the class of TQFTs that are labeled by homotopy classes of maps to BG, you're talking somehow about manifolds equipped with a G principal model.
Well, this was before gauging. This was invertible.
Yeah. Yes, it's just in the definition at the beginning. But I could in principle ask about something like KGN there, like some higher Heidelberg-MacLean thing.
Yes, sure. Yes, absolutely. Yeah.
Do you have some comments on what that would Like,
Yeah, high form gauge theory.
it should be something like
High
that.
form finite group gauge theory.
Like, could you apply these techniques to classify such things?
Absolutely.
Okay.
So, and mathematical question. So these groups which you're computing, this spin cobordism group for BG, they were known in mathematics only for points before? Or they
were only known for points and like BZ2. Well, okay, they were known for points, and they were secretly known for BZ2 to the K. I mean, you can find this stuff. But this thing is there is a book called Real Connective Case Theory of Finite Groups.
By whom?
Sorry, I forgot. Yeah. Yeah, there are examples like this, and for some, actually some non-abelian groups, but not the ones, not this kind of product of abelian groups actually. Yeah, this is new. This is new in math. That's why this was a theory.
Question out of left field. A few years ago, Kashayev defined some 4D TQFT that was based on some version of discrete quantum dialogue, and it computed numbers, and no one quite understood what it was. You didn't happen to.
I'm not sure if it's exactly, but I think some of his stuff can be related to this. Actually, this discrete two-form finite group this two-form gauge.
That was not spin. That's for sure.
Yeah, this
It's not spin.
It was not for projected modules also. So I'll comment on this a little bit.
Very impressive.
Well, on this note, let's.
Well,
again.